Math 2414, Parametric Curves, Video 11. One more example. And it is just that, one more example. There's plenty of rich exercises at the end of the homework assignment for the class that I'm currently teaching with the book that we're currently using. And if time was not an issue, I would spend some time going over them because they really expand your mind as a mathematician, whether it's applied or theoretical. But time is not on our side, so we'll just do one more example. For this example, we have x equals 4 cosine theta, y equals 2 sine theta, and theta is limited between 0 and 2 pi, which makes sense if you think about it, because both of these trig functions, their theta isn't tampered with, so they both have a period of 2 pi. So this range of of theta values should give us our entire graph. Now, after we sketch the graph manually, we will attempt to eliminate the parameter, and for some of you, introduce you to a new type of equation and curve. All right, I've already got two tables set up representing what we're going to discover in quadrants 1 and quadrants 2. Quadrants 1 and 2. Quadrants 3 and 4 will follow suit, so when you see them, it'll be pretty easy to figure out what happens. And I did pick our convenient values of pi so that we don't have to resort to Excel, because you should know your trig functions for these. So we're going to fill these out fairly quickly, starting with the x's. Let's just do the x's first. 4 times cosine of 0. Cosine of 0 is 1. 4 times 1 is 4. 4 times cosine of pi over 6. Cosine of pi over 6 is the square root of 3 over 2. The square root of 3 over 2 times 4 is 2 square root of 3. I didn't need to write it to figure it out, but I wanted you to see it. Make that 2 a little bit better. All right, 4 times cosine of pi over 4. Cosine of pi over 4 is the square root of 2 over 2. If we multiply that by 4, we get 2 square root of 2. At some point, we're probably going to want some decimal approximations to help us plot these. 4 times cosine of pi over 3. Cosine of pi over 3 is a half. 4 times a half is 2. And then 4 times cosine of pi over 2. Cosine of pi over 2 is 0. 4 times 0 is 0. Knowing what I know about trig functions and what you should know about trig functions, you know that cosine oscillates between 1 and -1, but because of the 4 in front, it's oscillating between 4 and -4. It's currently plummeted from 4 to 0, so the next path it will go is continuing into negatives, but it'll repeat the same values, just negatively. So -2, -2 square root of 2, -2 square root of 3, and -4. This is assuming that you've chosen your thetas conveniently. And I did because 2 pi over 3, 3 pi over 4, 5 pi over 6, and not 2 pi, excuse me, pi are the stops along the unit circle in quadrant 2. Now for the y, we're doing 2 sine of theta. Sine of 0 is 0. 2 times 0 is 0. Sine of pi over 6 is a half. 2 times a half is 1. Sine of pi over 4 is the square root of 2 over 2. The square root of 2 over 2 times 2 is just the square root of 2. And sine of pi over 3 is square root of 3 over 2. Square root of 3 over 2 times 2 is just the square root of 3. Oh, and sine of pi over 2 is 1. 2 times 1 is 2. Just like cosine, sine oscillates between 1 and -1, but this sine has a 2 in front of it, which doubles the amplitude. And so it's oscillating between 2 and -2. This has just gone from its middle to its top, and now it's gone from the middle up to 2, and now it's about to go back down through the same numbers, but they'll be positive this time. Square root of 3, square root of 2, 1, 0. All right, let's plot these. But before we do, let's get some decimal equivalents. The square root of 3 is approximately 0.86. So we have a 2 times the square root of 3. So if we double that, we get 1.62 approximately, 1.72. And we even have, oh no, we don't need to double it. Oh, what am I doing? Square root of 3 can't be that. That's square root of 3 over 2. Square root of 3 is about, I want to say it's about 1.72, but let's just make sure. 3 square root u, and we get about 1.73. Sorry, my brain was thinking square root of 3 over 2. If we double that, we'll get about 3.46. The square root of 2 is about 1.41, and so if we double that, we get 2.82. So those decimal equivalents will help us plot these pretty quickly. I will be going back and forth between this table and this graph quite a bit. All right, our first point is 4, 0, so we're starting over here. Our second point is 2 squared of 3, 1. So 3.46, 1. 3.46 is about halfway between, up 1. Okay, now we're right here, 2 squared of 2, 2. So we are at 2.82, 1.41. 2.82 is about here, 1.41 is about right here. Okay. I'm gonna check something real quick. Being a little persnickety here, but I think that second dot needs to be just a little bit more over to the right. And I know what you're thinking. You're really arguing accuracy with these decimals on this hand-drawn graph. But the thing is, I already know what the graph's gonna look like. All right, so we're on the fourth point. The fourth point is 2, square root of 3. So it's 2, 1.73. 2, 1.73 over 2, up 1 and almost 3/4. So right about there. And then the next one should be 2, 0, 2. It is. Okay. Now, I won't have to go back and forth anymore, because if you look at these ordered pairs, let's use a different color. If you look at these ordered pairs, they are the exact same as these, just going in reverse with the x being negative. So I get the mirror images of these points across the y-axis. Now you could plot them all manually if you wanted to, but I don't need to. About there. Dot, please, not that thing. Well, I'm going to look at them. -2, square root of 3, back 2, up about 1 3/4. -2 square root of 2, square root of 2. So -2.82, up 1.41-ish, about there. -2 square root of 3, 1. So -3.46, 1. And then here. And if we connect these points, we get a nice little ellipse. And the orientation is going counterclockwise. If we were to continue with quadrants 3 and 4, we would get the exact same phenomena down here. And we get what's called an ellipse. Now, I haven't given you the formal definition of an ellipse. Think of it as a circle where the radius in one direction is different than the radius in another direction. Specifically, there's what I would call an x radius and a y radius. Technically speaking, they are called the minor and major axes, plural of axis. But the important thing is this crosses the x-axis at 4 and -4, the y-axis at 2 and -2. And it's not a coincidence, because 4 was the coefficient of cosine and 2 was the coefficient of sine. Now, we're going to verify this in Desmos in just a moment, but I would like to go ahead and try to eliminate the parameter. Now, we've eliminated parameters of sines and cosines before, but these sines and cosines have coefficients, 4 and 2 respectively. The identity that ties them together is cosine squared plus sine squared equals 1. So before I square, I want to isolate each trig function by dividing the first one by 4, the first equation by 4, and the second equation by 2. Then if I square everything, I get x squared over 16 equals cosine squared theta, y squared over 4 equals sine squared theta. And because sine squared plus cosine squared equals 1, I know that the sum of these has to equal 1. Therefore, our equation is x squared over 16 plus y squared over 4 is equal to 1. And let's verify it all in Desmos. There you are. All right, so let's start with our parametric equations, which were 4 cosine of t and 2 sine of t. Okay, let's make our interval go all the way to 2 pi. There's our ellipse with the intercept of the x-intercepts at 4 and -4 and the y-intercepts at 2 and -2. Just for kicks and giggles, we're going to send this little point around here. I said kicks. Back, stop. Something traveling through space in an ellipse. Gee, I wonder what things do that. Well, pretty much every planet in the solar system. And we claim that this is the same as x squared over 16 plus y squared over 4 is equal to 1. And if we turn that graph on, we'll see that it indeed is. All right, I want to wrap up this video and this series of videos with one quick comment, not necessarily about parametric equations, but about ellipses. This is an equation you really need to have in your arsenal if you don't have it already. An equation of the form x squared over a squared plus y squared over b squared equals 1 is an ellipse. The x-intercepts are a comma 0 and -a comma 0. The y-intercepts are 0 comma b and 0 comma -b. There's a lot more to an ellipse than just this. There's 2 foci, there's something called an eccentricity. There are some physical properties of an ellipse. Without going into details, there's 2 points in the middle along the major axis, where if you were to send a light ray, it would reflect and hit the other point, no matter which direction you sent it in. If you've ever been to the whispering room in the Oval Office, it's an ellipse. You can stand at either point. 2 people at either point, you can whisper and hear the other person, no matter which direction they face. My battery is running low. That's a sign I need to end. All right, well, that's the end of this section, but it's not the end of parametric equations, because the next series of videos will be calculus with parametric curves.